Hey everybody, I just wanted to take a moment and go over the results of your experiment. Wanted to talk about it and maybe define a couple of new physics terms for you. So here goes. This was trial one's data, so if you did trial one, you probably got something pretty similar to this. If you did a different trial, I'm sure it looked a lot different. Even if you did do trial one, you probably got slightly different values for things. So the world's an imperfect place. Looking at this, you were asked some questions in the lab. One of them was, what does the slope of one of these graphs represent? What does the intercept on one of these lines represent? Let's look at the slope first. The slope of a line would be the change in position. I used x to represent position. That'd be the rise, divided by the run, which is the change in time. So this is the change in position, how much the position of the ball changed in a certain amount of time. Well, if you actually do that calculation, here's the red ball. If you actually do that calculation, you're going to get something that's similar to this, 39.1 centimeters per second. So for every second, this ball's position changes by 39.1 centimeters. So what's that actually saying about the red ball? Well, it's sort of like how fast it's going. We have a name for it in physics. We call that the velocity. So if you want to actually define a term, velocity is the slope of a position versus, sorry about the chicken scratch, position versus time graph. In terms of variables and an equation, well, I found the slope and I called that velocity. So V, and I'm going to say average velocity. So the average velocity over a certain interval of time is the change in position divided by the change in time. That's the slope of this graph. Another term I would like to go over with you is this one right here, change in position. We can say change in position, but in physics we often use a different word for change in position. We use the word displacement. So technically speaking, you would find an average velocity by finding the displacement or change in position and dividing it by how long it took. The word displacement kind of makes sense if you think about it. If it began at a certain spot and it ended up at a different spot, so over this time interval, the object began at this position and ended at this position, it was displaced. It got moved. That's how big its change in position was. Anytime you find a displacement or a change in anything for that matter, you have to make sure that you subtract things in the right order. A change in anything is final minus initial. So in this case, it would be the final position minus the initial position at the start of the time interval. So this would be like the initial position, and that would be the final position at the end of the time interval. Final minus initial, always do that. It doesn't matter if you're doing a change in temperature, a change in mass, it doesn't really matter. You always take a final minus an initial. You probably remember that from your glory days back in IPS. So that's how you find velocity. And here's a new term for you as well. Remember, displacement means change in position. I also did this, wrote equations for the other two, giving you three altogether. In this particular trial, interestingly, the white ball, this one, started the furthest to the right. So what does this intercept actually mean? It's the starting position. It's the initial position of the ball at a time of 0. It started with the greatest initial position, but in this case it actually finished in last place. Well, why is that? Well, it started to the right, but look, it had the smallest velocity. It went actually the slowest. The red ball, which was the winner, not only had the biggest velocity, the biggest was the red in this case, but it started a little bit to the right of the origin. This one, the blue, started at the origin and had a pretty big velocity, but wasn't enough. Never caught up. Another graph that we could use to portray the motion of these things, this is a position graph. We could also graph the velocity of these things over time. Now, look at this. These things traveled very steadily. There's a consistent amount of rise for every amount of run. So this velocity versus time graph has to show that three objects moved with very steady velocities. Here's what that would look like. Now, where did I get these values? Notice they're just horizontal lines, which would mean an unchanging velocity. Well, the blue, if you remember, the blue ball had a velocity of 37.5 centimeters per second. That was the slope of the position graph. So 37.5 centimeters per second steadily for the entire time. The red ball had a steady velocity of 39.1 centimeters per second. Didn't change. The white ball had a velocity steady of 23.6 centimeters per second. So this is a velocity graph, and later on when we start dealing with objects that accelerate, that change the way they move, these graphs won't be horizontal when you look at a velocity graph. You know, if it's accelerating or going faster, it might be sloped upwards, or if it's going slower, it might be sloped downwards, something like that. But we'll get to all of that later. Another thing I want you to realize about these velocity graphs, if you look back at the meaning of velocity, excuse me, velocity is displacement over time. Well, I could rearrange this and I could actually solve it for displacement if I wanted to. So let's take that same equation. Average velocity is displacement over time. If I solve it for displacement, if I want to know how far that thing went and what way, here's what I could do. Multiply each side by time. And I'd get this. Displacement equals, I'm going to reorder it, the average velocity times the time, right? Look back at this graph. Here's an interesting graphical relationship. Those of you who are in calculus are going to be doing quite a bit with this. Average velocity is the height of this shape right here. I'm going to shade in an area. Look at this equation. I've shaded in an area, and this happens to be a rectangle. That rectangle has a height of, looking at my data, this is actually 23.6 centimeters per second. And it's got a width of 2.0 seconds. So look here, this is actually the height of my rectangle. This is actually the base or the width of my rectangle. So 23.6 times 2.0 seconds equals displacement. So 23.6 times 2, that'd be 47.2. Look what happens to the units. Centimeters. Here's what I would know. In 2 seconds of going 23.6 centimeters per second, this thing would have moved 47.2 centimeters. The moral of the story is this area that I've shaded in actually represents the displacement of the object. The area under a graph of velocity versus time represents displacement. And you can do this over any interval you want. I could have shaded in a different area for a different interval of time. I could use this idea to figure out how far the blue ball went from 0.5 to 2. I would simply shade in this area, figure out how tall it is, figure out how wide it is, multiply them. That area would represent how far the blue ball went between 0.5 and 2 seconds. So kind of a neat graphical relationship. The area under a velocity graph really does represent how far the object went.